as we would normally cover it, but such is life. All right, so 2.2, we are talking about our quadratic function. These you're most often going to see written in the form of ax squared plus bx plus c, which is what I kind of like to call the useless version of the quadratic. A, B, and C. The A tells you a little bit, but the B and C just kind of on their own don't really do very much to kind of instruct us what is actually going on with this function. Thank you. And so to that end, not really kind of the most beneficial, not really the most relevant way to think about our quadratic. Unfortunately, though, the most common kind of presentation that you are going to get. So when we are thinking about quadratics, these are our functions. We've looked at a couple examples of this. Really liked to use this as like what we were doing with the transformations. So for f of x equal to our most generic quadratic here, going to be x squared. And looking something like this. And all of them will have this kind of same general shape of this U starting from some kind of center point. Couple of things to note about our quadratic. First of all, our parent function here is even. Not all quadratics are going to be even functions, but all of them are going to be symmetric around some kind of axis. That axis, very creatively named, the axis of symmetry. You could think of this as like the line about which our quadratic is symmetric. In the case of our parent function here, this is just going to be the y-axis. Now, as far as the equations for these kind of vertical lines go, remember that in this case, we are fixing the value of x and letting the y value be whatever it wants to be. And so we would say that the axis of symmetry here is going to be the line x equals 0. If you just told me that the axis of symmetry is 0, it is wrong. It needs to be the line x equals 0. We are saying it is x equals 0 because that x value is like the only thing that's kind of set in stone. The y value is allowed to be whatever it wants to be, which is how we get a vertical line. The other key feature of our quadratic that we are going to focus on, well, one of the other ones, there's one other thing that we actually care about with regard to our quadratics. But one of the other key ones is going to be the vertex of our quadratic. You can kind of think of the vertex as being the center of the quadratic. I think that that's not a horrible way to think. It's also going to be the minimum value or the minimum point, the maximum point on that quadratic, depending on whether we are facing up like this one. We could also picture a quadratic that kind of dips down as well, in which case our vertex would be the maximum value that we achieve. But regardless, either way, what we are looking at is this kind of value at which our function is either minimized or maximized, which we can think of as like the center of our function, right? Now, in this case, our center is 0, 0. We're going to see why that's relevant here in a second. In particular, this is going to be relevant because what we are going to do to our quadratic, very similar to what we did in 1.6, kind of applying that transformation, like that general transformation idea to this very specific function. what we can get is a modified version of our quadratic that is essentially just a whole bunch of vertical shifts, horizontal shifts. In other words, we could take our parent function here and call it, we'll say like f hat of x, which will be just our shifts applied to our quadratic. So in this case, think of this function as x minus h squared plus k. That's just vertical shift, horizontal shift. And we can think of what this shift does. This is going to take our vertex from 0, 0 and move it to our new location at h comma k. This is going to take our axis of symmetry at x equals 0, move it to a new location. In this case, it's always going to track the x value around which we are centered. So moving this to x equals h. And this kind of formatting is a lot more useful than standard form. This gives you a really clear idea. Where is our function centered? What is kind of the behavior going around this function? How can I take my very simple parent function and apply these kind of very basic transformations to it in order to arrive at the function that I actually care about? This is often referred to as vertex form because you very instantly can get the vertex from this formula just for free. It's h and h comma k. But you can also think of it as very much being like our transformed function. These are just vertical, horizontal shifts. Now, in tandem with this, what you will often see with vertex form is that they stick this kind of a out in front. That's just to account for any like stretches or compressions as well. So the vertex part of it is the h and the k, but the a is just to say, okay, are we going to be like a skinnier quadratic, or are we going to be a wider quadratic? That all is just going to depend on a. Are we going to flip upside down if a is negative? All that fun stuff. Okay, so vertex form, this is the first of what I would say is of like two useful forms for our function. But like I kind of said before, we're going to be given the useless form. And so it'd be very, very helpful to have some kind of way to take our useless form, this ax squared plus bx plus c, and turn it into our vertex form. Find those values of h and k that we actually care about. Okay, so a little bit of algebra on the right-hand side of this equation in order to see that these are equal. So what I am going to do is I am going to actually apply that squared and see where that takes me. So applying that squared, you can kind of do this in your own time if you would like. But when you do out the Punnett square, you should get something that looks like a times x squared minus 2hx plus h squared plus k. And distributing that value of a through, what we end up with is ax squared minus 2ahx plus ah squared plus k. Okay, why on earth have we done this? Why have we taken our kind of nice compact form and written it out in this way? Well, it is to make clear kind of the connections that we have between what we will be given and what we actually want to see. Couple of things that I would like to observe. First and foremost, this value of a and this value of a have to be the same. Because it's the only thing that's sitting in front of x squared. So the a in our original equation and the a in the useful modified equation are going to be the same values. That's already one kind of piece that's very useful. The second thing is, what is this value of b going to be equal to? Well, if we look to the coefficient in front of x here, we can see that b should line up with this negative 2AH piece. That is the coefficient in front of x. And one final question, not one that's particularly relevant, but I will show you anyway because we can do it. What is the c going to be equal to? Well, c should just be everything that doesn't have an x, which in the case of our function, that is this ah squared plus k piece. Okay. Why are we making these connections? Well, it is actually very, very specifically for one equation. And that equation is that b should be equal to negative 2 times ah. Why is this equation so useful? Because if we solve for the actual value that we care about, we don't care about b, we don't really care all that much about a. What we care about really here is figuring out what is h. Solving for h, we get that h should be equal to b divided by negative 2a. And this is our way of taking that useless information, that ax squared plus bx plus c, and using it to get information that we actually care about. What is the value of h? What is that vertical, or not vertical, what is that horizontal shift going to be? Now, you guys have probably seen this. It's probably been given to you in the form negative b over 2a. And that's fine. You can stick the negative wherever you want. It doesn't matter. It can be on the outside. It can be in the numerator. It can be in the denominator. All of that is equivalent. I write mine as in the denominator because it comes from dividing both sides by negative 2a. But again, it doesn't matter. You can have that negative be anywhere in that formula, and that's totally fine. We could construct a similar formula for k. And I have seen some people use this. I generally don't. In this case, we could say, for instance, that c should be equal to ah squared plus k, and that k should be equal to like c minus ah squared. So if we find h, then we can find k, and that's certainly true. This certainly would work. You generally don't see that, though. Main reason, it's just easier to do it a different way. In particular, if h comma k, if this combination is a point on our parabola, then how do I find my y value when I'm given a particular x value? You just plug it into your function. So more often than not, we'll just say that k is equal to our function evaluated at h. We'll just plug h in for x, and that'll also give us k. But there is kind of this equivalent way to find k, similar to how we found h. I think I've seen like 3 people use this out of like my 300 students that I've had. So if you want to, it is there for you. But I generally don't really advertise or recommend memorizing an extra formula when you can just plug the value into the function, and that's that easy. But it does work. You can test it. It'll always work. So. Any questions here? Okay, Let's see this in action. We are given a bunch of functions in our useless form. Our goal is going to be to write them in our useful form, write them in our vertex form here. So we need the values of, technically we need the value of a, but we're just going to be given that instantly, so that's fine. And then we need what is h, what is k. So looking at our example 1a here, what are the values of a, b, and c that we are given? Very good. The value of c doesn't really matter here. It can, again, you can use it to solve for k. We don't need it, but you know, it's there. Very good. Okay, what is our formula for h? How do I find h? Say again. What is our formula for h? What's the general form? b over negative 2a. What is our value of b in this case? Negative 4 over negative 2 times 1, which is going to equal positive 2. 2 over 1. All right. How do we find k? Well, you could memorize that formula. Again, you don't need to. K is just f of h, which we already know what h is. H is just 2. So this is f of 2. What is our function evaluated at 2? Well, this is going to be equal to 2 squared minus 4 times 2 minus 12. 2 squared is 4. 4 minus 8 is going to be negative 4. Negative 4 minus 12, I get here negative 16. And that's all the information we need. So what is our function? Well, f of x is going to be equal to a, but what is our value of a here? Found that right at the beginning. A is just 1 times x minus h, so x minus 2 squared plus k minus, so that'll be minus 16. And this is our vertex form.
You get k equals f of 2.
I am telling you that you can find the value of k by taking the value of h and plugging it into your function.
So you got the 2 from that?
Yeah, the 2, so the 2 is the value of h, and we're taking the value of h, plugging it into our function. You also could, if you wanted to, use the formula k is equal to c minus ah squared, and you would also get negative 16. Yeah. You do not need to. I'm just trying to show you all the pieces getting plugged in. Just so it's very, very clear kind of what I'm doing. Okay, now that's not the full problem, right? The other part of the problem is identifying the axis of symmetry. Good news for us is that the axis of symmetry is always just going to be following whatever that value of h is. In this case, the axis of symmetry, h we said is 2, so that's going to be the line x is equal to 2. So it'll be positive 2 to negative 16. The reason why we see that minus 2 is because the x flips when we do that transformation. That x shift flip-flops. But yeah, absolutely. As far as the vertex goes, that point is 2, negative 16. All right. Any questions here with example 1? Okay. Let us continue on then. So vertex form is kind of the first of our useful ways to think about our quadratic. The second is going to be the factored form of our quadratic. So in other words, taking our ax squared plus bx plus c and rewriting it as like x plus some value. We'll call it, I don't know, we'll call it, what's a nice easy one? We'll call it like k sub 1 times x plus some value k sub 2. This idea here of taking our general form and splitting it up into a product of factors like this is very universal. These factors are also called roots. So the roots of our quadratic are going to be the factors x plus k1 and x plus k2, where k1 and k2 are just complex numbers. Right? So really no restriction on these at all. They can be imaginary, they can be complex, they can just be real. So a quick point that I would like to make: when we are talking about finding the roots of a quadratic and ultimately later on a polynomial, this is what we're looking for. We're looking for x plus something or x minus something, and that is the root. When we are looking for the zeros of the quadratic, it is the value of x that we would plug into a root that would make it 0. So the root is like exactly what we see here. The 0 is the value of x. So in this case, the 0 would be like negative k sub 1 or negative k sub 2. And then the x-intercept is the point on our graph that corresponds to a root or a 0. So 3 different objects. These are words that are used pretty interchangeably. So like finding the root, finding the x-intercept, finding the 0. Your process is pretty much the same across the board, but just kind of tuck away in the back of your head. The x-intercept or x-intercepts are going to be points. The zeros are going to be some value of x. And then the root is like this weird piece of our equation here, this x plus some 0, or the negative of some 0. Also, my writing it as plus is mostly to make the next little bit of algebra that we do a little bit cleaner. It's kind of poor form because we'll see later on that we will want it to be negative. We will want the opposite sign that we have in solving for the zeros. So slightly poor form, but it'll make the algebra a little bit cleaner with what we're doing here. So exactly like before, we want to figure out, well, we've got this useless information. How can I use this useless information in order to find these 2 zeros or these x-intercepts or whatever? So multiplying out, doing out this Punnett square, again, you're more than welcome to attempt this on your own. But what I end up with is x squared plus k1 plus k2 times x plus k1 times k2. Actually, let me back this over. So this is and so very similarly to what we were doing before, what kind of equations can we generate from that? Well, b is going to then be equal to our k1 plus k2, our 2 zeros kind of added together, these 2 values added together, and c is going to be, well, really, I keep messing this up, but that's fine. We can think of them as the product of these values. I do want to make a quick note, which is that it would have been better form for me to have an A out here, kind of like what we did before. And when I have an A out here, where we see that A is particularly with C. Technically, it's there throughout all of them, but we'll see an example like this later on where A times C is really going to get us kind of the trick that we want. But again, we'll talk about that momentarily. So when we're factoring, why do we care about this? What does this tell us? Well, it tells us that the question that we want to ask is what are the two numbers that add to make B that multiply to make C? This is that whole factoring question that we've asked over and over and over again. What are the two numbers that add to make B that multiply to make C? And here's why we ask that question. It's because B is equal to the sum of those two numbers. C is equal to the product of those two numbers. So for instance, let's take a look at 2A here. What are the two numbers that multiply to make negative 15 that add to make positive 2? Say again? Negative 3 and positive 5. And so what do we do with those numbers? That tells us what that 2x should really be written as. So in this case, we might say that really this is x squared plus 5x minus 3x minus 15 equals 0. Okay. We are then going to group our two are like four kind of pieces. The order in which we do this doesn't matter. You should end up with the exact same thing. And then we are going to GCF factor each group. So for instance, looking at these first two terms, what is the greatest common factor that we see? An x. So we bring an x out to the front. If I am pulling an x out to the front, what gets left behind from my x squared? An x. And what gets left behind from my 5x? A 5. Looking at my second two terms, what is my GCF? So in this case, we're going to say it's negative 3, just because we want to pull out a negative from that front. That's just convention. You're always going to factor a negative out if you see your first term there is negative. So bringing a negative 3 out to the front, what are we left behind with? Well, negative 3x will become an x. Negative 15 will become a positive 5. This is no coincidence that these two match. These two need to match. It's not a coincidence. They must match. You need to get the same thing. Okay, second round of GCF factoring. What factor do these two numbers share? Not 5. Not negative 5. What did we say, Dylan? They share an x plus 5 as a factor. So taking that x plus 5, bringing it out to the front. From x times x plus 5, what am I left with? I'm left with an x, and then from the negative 3, I'm left with a negative 3. And this is still equal to 0. Okay, so I have some number a times some number b is equal to 0. If I multiply two numbers together and I get 0, what must be true? At least one of them has to be 0. So this is either going to be true if x plus 5 equals 0, or if x minus 3 equals 0. What are the values of x where that is going to be true? Solving for x, I get that x must be negative 5, or that x must be positive 3. Let's look at one that's maybe a little bit trickier. The nice thing about this technique, there is a way once we answer that question to jump straight from what we're given here down here. But the nice thing about doing it this way is that we don't really care if there's a coefficient in front of the x squared. We deal with it the exact same way. That's kind of the utility behind this. The only thing that you need to remember, and it's not even really something that's different, it's something we do in A, we just don't talk about it, is that what we're comparing is not really the things that multiply to make B and C that add to make, that multiply to make C that add to make B. It's the things that multiply to make A times C. In this case, notice that A times C is just C because A is 1. But when we have a coefficient in front of the x squared, that C, that thing that we multiply to make, switches from just C to A times C. So in this case, what are the two numbers that multiply to make negative 18 that add to make positive 7? 9 and negative 2. And so we take that 7x, we split it up. This is going to be plus 9x minus 2x minus 6. We do the exact same thing we did before. We GCF factor. In this case, the GCF of my first group is 3x, leaving behind an x plus 3, and the GCF of my second group, negative 2, leaving behind an x plus 3. And factoring out that x plus 3 shared factor to the front, we end up with x plus 3 times 3x minus 2 equals 0. And from there, it's the exact same thing. You set them both equal to 0, solve for x, so on. All right, questions here with example 2.
So how do you do the last part when if it's 3x
minus 2? Yes, so 3x minus 2. So you do the exact same thing. So we have two numbers multiplying together to get 0. So that either means that x plus 3 equals 0, or that 3x minus 2 equals 0. Yeah, so for our top equation, subtracting 3 from both sides, we get that x should be negative 3. And for our bottom equation, adding 2 to both sides and then dividing by 3, I get that x should be positive 2/3. So adding 2 and then dividing by 3. We're not looking for the vertex here. We're just looking for the solutions to this equation, which would be what we see here. The vertex from this information actually isn't super hard to figure out. The vertex is the point that falls right in the middle of our x-intercepts. So you could take the average of the x-intercepts, and that would give you the value of h. It would be a little bit nasty in this case because we've got 2/3 as one of those values of x. So it's going to be like something in terms of sixths probably. But we certainly could find the vertex from here. We just are not looking for it.
So
Yeah.
if you added the plus 2 to the 3x, would it make it a 5x and then you divide it by 3?
No, so we're adding the plus 2 to both sides to cancel out the minus 2 on our left-hand side. And so we would end up with 3x equals, I'm not writing the highlighter. We would end up with that 3x equals 2. So adding 2 to both sides. And then divide by 3. You got that x is equal to that 2/3. Yeah, Dylan. Probably. I mean, not necessarily. Again, you could find h by just taking the average of those two x values. That would work. That would give you h. And then you would need to plug in to get the y. But like ultimately, if you wanted to do that or the negative b over 2a, either way, it's going to be a little bit messy. In particular here, it's what, like negative 7 over 6. Yeah. I guess it does say identify the vertex. Yeah. 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 So a little bit messy, but yeah, you certainly could. Either way, it's fine. You can find the value of h by doing that negative b over 2a thing, or you could find the value of h by making the observation that h sits perfectly in the middle of those two x values that we just found. And either way should get you to the right answer.
Decimals?
Yes. Oh yeah, we're about to get numbers worse than decimals too here momentarily. Okay. So that's all great. That is only, though, going to work for particular functions that are nice to solve, which, most functions are not going to be particularly kind to solve. In particular, there are going to be plenty of equations that we're going to run into where there isn't an answer to that question. What are two numbers that multiply to make C that add to make B? Looking at 3a, what are two numbers that multiply to make 5 that add to make 2? There aren't any that we can think of. And so this would be one where we can't really approach it in the same way as the one before, but that is okay. We have a kind of monkey wrench of a tool that will just allow us to solve any of these problems regardless. You could even use it to solve the other ones. You would just get nice answers, which is fine. And that is our quadratic formula. Quadratic formula says that x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And we look at this and we think, man, this formula looks terrible. It's got so much stuff going on. But you look at it a little bit closer and you see actually some of these pieces are things that we've already seen before. For instance, if I split apart this fraction, I'd get negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. What is this? Yeah, it's the x value of the vertex. This is just h. And so what are we doing? Well, we're taking h and we're moving a little bit to the left and we're moving a little bit to the right. And however much we had to move a little bit to the left or a little bit to the right tells us exactly what we have going on here. This is like our error term, and we're shifting slightly to the left, slightly to the right. There's some very cool geometric kind of constructions that show us where this kind of movement actually comes from. We are not going over that. This is really just supposed to be a quick overview as to kind of what's going on here. All right, so just kind of things to note if you want help remembering this formula. It's got a lot of similarity to what we were doing before with the negative b over 2a. Or maybe not a lot, but it has a fair bit of similarity. But this is just a nice formula that allows us to take any quadratic and instantly find the, maybe not instantly, but very routinely find the zeros. So for instance, looking at 3a, what are our values of a, b, and c going to be equal to? 1, 2, and 5. And so plugging into our formula, we get that x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Simplify this down a little bit. 2 squared is 4 minus 4 times 1 times 5 is going to be 20. So this is x is equal to negative 2 plus or minus the square root of I get negative 16. All divided by, well, hold on, 2 times a, we know what a is. A is just 1. And then what is the square root of negative 16? 4i, very good. Not 2a, we already figured out what a is. And that would be a reasonable place to stop. You could definitely be done there. We can make it look a little bit prettier. In particular, this gives us 2 solutions. This tells us that x is equal to -1 plus 2i and -1 minus 2i. But like, this is perfectly fine. That's great. Notice in this case, we got 2 complex zeros. Implication there being that we don't have real x-intercepts, that we are hovering above our x-axis, it's kind of like that. And so this would be a great case of a quadratic that does have roots, does have complex zeros, does not have x-intercepts. So we can see, well, really, those 3 terms used to really mean the same thing don't quite mean the same thing. All right, any questions with quadratics? How are you feeling? I'll take your silence as an outstanding. We'll continue right along. Okay, quadratics are a very specific version of what we are actually going to be focusing on during the rest of Unit 2, or at least for the most part, the rest of Unit 2, and that is the polynomial function. So the polynomial function, we can write any polynomial in the form of a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus all the way down to a sub 1 times x plus a sub 0. Okay. Now this looks, again, kind of long and confusing and complicated, and man, where are any of the numbers in that? But let's break down kind of what we have here. First thing to note, this is the sum of a bunch of powers of x. In particular, these are whole number powers of x. So n is only ever going to be allowed to be a whole number, and you're only ever going to see like x to the 5th, or x to the 7th, or x to the 102nd. You're never going to see like x to the 1/2, or x to the -3rd, or things like that. Because of this, do we ever need to worry about dividing by 0? No. Dividing by 0 would be like 1 over x, which is x to the -1. We don't really need to worry about that because, again, our powers are only going to be positive. Do we ever have to worry about taking the square root of a negative? Also no. The square root of x is equal to x to the 1/2. And since our powers can only be whole numbers, we also don't need to worry about that. If we don't need to worry about dividing by 0, if we don't need to worry about taking a square root of a negative, what is the domain of this function? all real numbers, or negative infinity to positive infinity. Now, the range of this function is going to depend a lot on a couple of different things. That's really what the focus of the rest of today is going to be on. We've seen polynomials where the range is all real numbers. Lines, for example, are polynomials. It's like x to the first plus some number. Lines are examples of polynomials that have a range of all real numbers. And we've seen polynomials that don't have a range of all real numbers. Quadratics have a maximum or a minimum value. That means that they don't hit every y value. And so it's largely going to depend, and in particular, what it is going to depend on is the degree of the polynomial, which very simply is just whatever n is. Or we could think of it as being whatever the largest exponent is. So thinking back to our quadratics, that would be a second degree polynomial because the highest power is squared. For a cubic function, it would be a third degree polynomial because the highest power is cubed. Linear function would be a first degree polynomial because the highest power is x to the first. We do technically here have like a zeroth power. You could think of there being like this implied x to the 0 here attached to this last term, because what is x to the power of 0? It's just 1. So we don't really write x to the power of 0, but do note that it is still kind of a power of x. And in fact, it is still a whole number power of x. 0 is still a whole number. All right. Now, the really nice thing is, at the very least, from a very, very zoomed out perspective. So when we are not focusing on the smaller values of x, from a very zoomed out perspective, figuring out what our function is doing is going to be fairly straightforward. My claim here is really that the function like x cubed compared to a function like x cubed plus, let's say, like 16,000 x squared plus maybe like 7 million x, that for a large enough value of x, they're going to be about the same thing. And that can be a little bit tricky, I think, to buy into. But first and foremost, I'd like to make the point, which is that the coefficients there, which I made look really big. I intentionally picked ones that looked really big on purpose to kind of garner this disbelief. They don't actually matter in terms of large values of x. I can pick a value of x that is large enough to make 7 million look like an absolutely tiny, pathetic number. Right? That's fairly easy. And so the difference between like 4x cubed versus like 12,000 x cubed, we certainly would see that difference a lot for particularly small values of x. But for very large values of x, the difference between these two is not as consequential as you would think. Right, so in terms of figuring out the general behavior, or when we are talking about large values of x, both positive and negative, we call this the end behavior of our polynomial. In order to talk about end behavior, we don't really care about the coefficients all that much. There's a little asterisk there. There's one piece of the coefficient that we actually care about, but the size of the coefficient doesn't matter. So then the next thing I'd like to convince you of is the fact that if we have x cubed versus x cubed plus x squared, that plus x squared also doesn't really matter all that much. And again, that's weird because, like, while 16,000 is going to be staying the same, and so the difference between having 16,000 versus like 7 million ultimately is going to become more and more insignificant, x squared grows and grows and grows, and it grows pretty quickly. And so we might think that by tacking on an extra x squared, that really we are changing the value of what we have pretty significantly, or that at the very least we could be changing the value of what we have pretty significantly. And that's not an unfair kind of conclusion to make. For instance, we could think of plugging into, say, a function like this, maybe like 10 to the power of 20. And we're cubing it. And the point that I'm trying to make is that that compared to, say, 10 to the power of 20 cubed plus 10 to the power of 20 squared is really not all that much. So let's think about this in terms of the actual numbers. 10 to the power of 20 cubed is 10 to the power of 60. This is an insane number. This number is so ridiculously large. This is a 1 with 60 zeros after it. It is an absurdly massive number. I think when you talk about like the number of like, I don't know, like atoms in the solar system or something like that, that you're starting to like get towards numbers that are like this large. So incomprehensibly large is the number that we are looking at right now. And we are comparing it to a number that's itself plus another number that is incomprehensibly large. This is 10 to the power of 40. In terms of the percent difference, what we are looking at is the difference between something like a trillion, which is 10 to the power of 12, versus, we'll say something like a trillion plus 10 to the negative 8. Just in terms of our kind of scope here, there is a magnitude difference of 20 between these two powers. And that difference is huge. This is like the difference between a trillion versus a trillion plus 1 over 100 million. Is there truly a significant difference between these two values? Not really. And for particularly large values of x, as you get even larger and larger, we would see that that difference is going to grow and grow and grow and grow. That the significance of this x squared term stops mattering. It doesn't have a particularly large impact on the values that we see. They just get too big to care. They get too big to care about what that x squared is actually contributing. Which is good news for us, because it means that if we want to understand the general shape or the end behavior of our function, the only thing we need to care about is what's going on out in front. The only thing that matters is, in this case, x cubed. The only thing that matters. Or the 4x cubed is the only thing that matters. Okay, so we have this long polynomial. We say, okay, well, really for end behavior, I'm only looking at what comes in front. What does that actually tell us? What kind of information does that give us? There are two different rules that we are going to follow. The first rule deals with what happens for large values of x that are positive. So we might describe this as what happens as x approaches positive infinity. So thinking plugging in like 10 to the 20, plugging in 10 to the 100, plugging in 10 to the 10 billion. Larger values of x. We use this kind of notation here to denote that we are getting closer to infinity in quotes. Our number is getting really large that we are plugging in. Are we actually getting closer to infinity? No, there's no such thing as getting close to infinity. That can't happen. But this is just kind of the script we use to communicate that idea that we are getting really large, specifically in the positive direction. So let's say I take a number that is positive and I raise it to some kind of power, right? Square it, cube it, raise it to the fourth, whatever. Does that change the type of number that I end up with? Thinking in this case, when I'm talking about type of number, I mean, is that going to change it whether it's positive or negative? No. So taking a number, raising it to a power, that in particular does not change whether it's positive or negative. What is going to impact whether it's positive or negative is the coefficient that lives out in front. So it's that a sub n that can dictate what happens as we go towards positive infinity. For instance, if I'm looking at negative 4x cubed, for a very large positive value of x, this value goes towards negative infinity. Versus something like positive 4x cubed, where for very large values of x, goes towards positive infinity. So this coefficient determines what happens as we approach positive infinity. In particular, if our leading coefficient is greater than 0, then our function follows suit, shoots up towards positive infinity. Whereas if our leading coefficient is less than 0, then our function flips on its head, shoots downward towards negative infinity. So that's our first rule. So first rule is we look at the coefficient, and if it's positive, then it tells us that as we move to the right, we're either going up, or if it's negative, as we're moving to the right, we go down. Think of like positive x squared versus negative x squared. That's telling us that we are moving either positive to the right or negative down. All based on just that kind of initial coefficient. The second rule that we have to look at deals with the power, the degree of the polynomial. For instance, if I want to compare x squared versus, let's say, like x cubed in terms of their behavior, how will these behave differently? Let's think about how they behave differently when I plug in a really large negative value. So for instance, if I plug in 10 to the 20 squared versus, we'll say, negative 10 to the 20 squared, what do I know about these two values? Ten to the 20 squared versus negative 10 to the 20 squared. What's going to be true about those two values? They're the same thing. In other words, our even-powered exponents don't care whether we are going towards positive infinity or negative infinity. We're going to see the same behavior. Whereas what would happen if I was comparing 10 to the 20 cubed versus negative 10 to the 20 cubed? What's going to happen here? The negative sign flips it upside down. These go in opposite directions. And so what can we gain from that? Well, we can say if our degree is even, then our ends will agree. That is to say, if our degree is even, then our function is going to be traveling in the same direction as its buddy. Whereas if the degrees are odd, particular if n is odd, then the ends disagree and go off in opposite directions. So 2 rules. And we're going to see where that takes us. We're going to see what that kind of lets us do. So looking at example 1a, we are trying to determine the end behavior for the particular polynomials that we are given. If what I said is true, we'll assume that it is for the purposes of this class. For 1a, what is the only thing that I really care about? Not just the exponent, I'm saying what term is the only one that I care about for 1a. There are 2 pieces to that term that we actually do care about. We'll care about the negative, but like what term? There are like 3 things being added together. Which one do I care about? Negative x to the 9th. And then what Oliver was saying, the 2 things that we actually want to look at, the exponent itself and the fact that it's negative. Okay. So according to rule 1, what happens as x goes to infinity? What does our function do? Is it going to positive infinity or negative infinity? Negative infinity, absolutely. And how do we know that? We have the negative out in front. So as x goes to infinity, our function goes towards negative infinity, and that is just because it is negative x to the 9th. It could have been negative 10x to the 9th. It could have been negative 3 billion x to the 9th. Doesn't matter. The fact that it's negative means we go towards negative infinity as x gets really, really big in the positive direction. What does the 9 tell us? What does that exponent of 9 tell us? So it's odd, which means are our n's going to agree or disagree? Disagree. And so we're going to do, as x goes towards negative infinity, we're going to do the opposite of whatever we saw us do as we went towards positive infinity. Our function as we went towards positive infinity approached negative infinity, and so we are doing the opposite in the opposite direction. So negative means that as we move to the right, as we approach positive infinity, we are going down. And the 9 tells us that our other end is doing the opposite of what we are doing. And that's it. That would be your answer. And this is actually, not only is it your answer, this is how you would write that answer. Okay, let's take a look at B here. What is the only thing that I care about? 3x squared is the only piece of this that I actually care about. Okay. What does the 3 tell me? What's going on as x goes towards infinity, and why? What is my function f of x doing? So we have positive 3, which means we are going towards positive infinity. Fantastic. And then what does my squared tell me? That our ends agree, and so our function is going to be doing the same thing in the other direction. In other words, in the positive direction, eventually, we don't really know when, our ends are going to look like this. And then in the negative direction, they are going to also look like this. And we have no idea what's going on in between, but we don't need to, at least for this. We'll flesh that out later. Questions with our end behavior? No questions? All right, one more thing then, and then we will call it for today. And that is really ultimately the kind of reason why, or one of the most important things that we're going to talk about, really just kind of scaffolding this idea. What we are working towards with Unit 2 is this idea that we can take any polynomial and, just like with quadratics, write it as the product of a bunch of roots. So we can take any kind of p of x and write it as some kind of a times x minus k1 times x minus k2, x minus k3, so on and so forth. And just like with quadratics, what this does is gives us a really, really good idea of what our function is doing in between those ends. So we look to the first term to say, ultimately, for large values of x, what is our function doing? We look to the roots to say, okay, for smaller values of x, how is our function behaving? Again, an idea that we will flesh out a lot more tomorrow and in the coming days. But this is kind of the idea that we're working towards, that we can take any polynomial, write it out as the product of its roots. And that has similar kind of utility to what we've been doing with quadratics, what we do with quadratics. Now, the good news for you guys, maybe the bad news, I don't know. I think it's good news, is that we, as just like not we in this class, but just we people, are really not that great at factoring things that are larger than quadratics. We are going to look at techniques that we will have later that allow us to deal with kind of not having a bunch of quadratics, but it's tricky. It is tricky. As soon as we get into a quadratic, we then have our quadratic formula. There is actually something called the cubic formula, which is just this absolutely nasty piece of work. Let me see here if I can't pull it up. So the cubic formula here, which, again, this is not something that that we will need in this course, but I just want to show you kind of what the alternative is to what we would be working with. So the very, very fun cubic formula, which is all of this. So it exists. We certainly could deal with cubic functions like this, but we're not going to, which is the good news. You do not need to know this. I have never needed to know this for anything. I just happen to know it exists because, that is my life, is knowing obscure math things. So we're never going to use that, but it does exist. So I think there is also a fourth degree one. There is famously not a fifth degree one. And not only is there not a fifth degree one, there can never be a fifth degree one. That was a very famous math proof that was done many, 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 many years ago by people infinitely smarter than I can even understand. So we do have the tools to be able to deal with higher level polynomials, but really anything above a quadratic gets to be pretty ridiculous. It gets to be almost instantly unreachable. And so we're just going to deal with how do we factor these things once we can get them down into a quadratic times some other product of various things. And then it's the exact same thing that we did with our quadratics. We take each of the individual pieces, set them equal to 0, run from there. So for instance, looking at 2a, look at how we have this whole kind of factored thing already done for us. That's fantastic. We have 4 numbers technically multiplied together to equal 0. So what must be true? at least one of them must be 0. And so we might say something like, this one's kind of redundant, but it did come up in first period, so I would like to mention it here. We would technically want to set up the equation 2 is equal to 0. We might say that x minus 4 should be equal to 0, that x plus 1 is equal to 0, and that 3x plus 7 is equal to 0. And then we would solve each of them for x. For 2 equals 0, are there any values of x that are ever going to make that true? No, we can just kind of throw that one away. It's worth saying that you can set up that equation. It just doesn't have any solutions. For x minus 4 equals 0, I get that x should equal 4. We are being asked for x-intercepts here, so that is the point 4, 0. For x plus 1 equals 0, subtracting 1 from both sides, we get -1, 0. And then subtracting 7, dividing by 3, I get -7 over 3, 0. Now we can do the exact same thing for b. It just requires a little bit more work. In this case, we'd actually have to factor out the quadratic that we were given. X squared plus 2x minus 8. What are two numbers that multiply to make -8 that add to make 2? -2 and 4. Very good. I'm going to kind of jump to the end here. This is going to be x times x plus 4 times x minus 2. And so what are the three equations that I get? Well, that is going to be that x is equal to 0. That is going to be that x plus 4 is equal to 0. And that is going to be that x minus 2 is equal to 0. And so my intercepts are 0, 0, -4, 0, and 2, 0. So pretty much the exact same thing that we were doing with our quadratics, except now we'll have a whole bunch more of them sometimes. And we'll look at that a little bit more. We're not going to be so helpless when we run into like a cubic function or a quartic function or things like that. Cubic is probably the reasonable limit of what I would ask you to be able to just do from scratch. But we will kind of refine our toolkit really in the pursuit of what are the zeros of this function. That kind of fleshing out what is happening in between my very, very large values of x. All right, we've got about 10 minutes left. We have the 2123 classwork that is due Tuesday next week at 11:59. Quiz for that would be that Wednesday. Extra credit, as far as the extra credit is concerned, make sure that you have the, what's going on here? Make sure that you have end meeting, please.